Hello again, my dear students, and welcome to the second part with the operational amplifier lecture. In the first part, we have discussed the difference between an ideal operational amplifier and a realistic one. And then we start together our first operational amplifier circuit, which was the inverting configuration. Today, we are going to investigate more in the inverting configuration. We are going to investigate what if the open loop gain is not equal to infinity. And then we are going also to discuss another circuit that can behave as an inverting configuration. And then we are going to demonstrate the non-inverting configuration. Now, please let me show my presentation slides and start our second part for lecture number one, operational amplifiers. Okay, say I think now you can see my presentation slides. I think so, and also I think we are now almost ready to start this lecture. Okay, perfect. Perfect. Let me now open my laser pointer as usual. Okay, let's do it. Okay, so if you remember, my dear student, in the previous lecture, we have investigated the operational amplifier. We say that we have this operational amplifier includes mainly 5 terminals, 2 input and 1 output, and 2 supply terminals. We said that these supply terminals will be somehow given within our course, so we assume that these supply terminals are connected all over the time. And then we say that the output is related to the input using what's called the open loop gain, where the V out equals to A times V2 minus V1. We have a negative terminal in the input, which called the inverting input, and we have a positive terminal, which called the non-inverting input in the operational amplifier. Then we discuss what's called the ideal operational amplifier. And whenever we have an ideal operational amplifier, then there's 5 important statements you have to remember whenever there is an ideal operational amplifier. First, that your input impedance will tend to infinity, your output impedance will tend to 0, your open loop gain will tend to infinity, which is A. So these are the 3 main assumptions. According to these 3 main assumptions, we have concluded that V2 will be equals to V1. I mean, the voltage drop on these 2 terminals are equal. And as far as the input impedance is equals to infinity, that means that the current going inside the operational amplifier is equals to 0. So these are the 5 main rules associated all the time whenever your operational amplifier is an ideal operational amplifier. Now, we discussed together in the previous lecture this circuit, which is a closed loop circuit. We have distinguished between what's called an open loop configuration, where there is no feedback signal or a feedback branch between the output and the input. Now we have a feedback branch between the output and the input with the resistance here called R2, and this is connected to the inverting terminal for the input. That's why we call this a closed loop configuration. For the closed loop configuration, we have an finite controllable gain. Again, for the open loop, your gain is A, ideally is equal to infinity, and this is uncontrollable value. This is a value associated to the operational amplifier. So you go to the market, you buy an operational amplifier, its gain, for example, is 50K, then it's a constant. However, whenever you have a closed loop configuration, we have concluded that the gain, which is V2 over V1, is equals to minus R2 over R1. So the first important feature for this gain is that this is a controllable gain. I mean, you can control the value of the gain by controlling the value of R2 and R1, which is a discrete separated resistance. You can easily vary its values. And also, there is another important point here, which is this negative sign. This negative signs mean that the configuration is an inverting configuration. So if you have an input positive voltage, you will get a negative output, and vice versa, of course. So that's why we call this the inverting configuration. Now, as a start of this next part, second part of this lecture, we are going to investigate what if we have the same circuit, but our gain is no longer equals to infinity. I mean the open loop gain, of course. Our open loop gain is no longer equals to infinity. Our open loop gain is equal to some finite value called A. What will happen? So first, whenever we have this, we have to recheck our 5 assumptions. Again, the first assumption is input impedance is equal to infinity. It is still equals to infinity. So your input current is still equals to 0. So these 2 assumptions are still valid. Your output resistance is equals to 0. So the output resistance is still equal to 0. This is again a fixed assumption for this. However, now the open loop gain is no longer equal to infinity. And if you remember, using the information that the open loop gain is equals to infinity, we have proved that V2 should be equals to V1. So again, from here. So as far as the input, the open loop gain is not equals to infinity, that automatically means that V2 now is not equals to V1, because A has a finite value, so V2 minus V1 will be equal V output over A and not equals to infinity. So what we are going to do now is that we are going to resolve this circuit, this inverting configuration circuit, but while considering that the open loop gain not equals to infinity and V2 not equals to V1. Okay, perfect. So what we are going to do now again, we are going to resolve this circuit while considering that the open loop gain is not equal to infinity and V2 is not equal to V. This is what we are going to do now. So let's now start this while considering a finite open loop. Okay, so now back to our whiteboard and let's start plotting the circuit. So we have our operational amplifier. The positive terminal is connected to the ground. The negative terminal is connected to a resistance called R1. And then we have our input voltage, which is Vin. And here we have another resistance, and then this V out. And this is R2. This is basically the configuration we are using, which is the inverting configuration. Now we are going to solve this circuit, but again, now we have a finite open loop gain called A, and we are not able to say that V2 is equals to V1 because A is a finite value. So what we are going to do? Okay, perfect. Let's now start thinking on the steps that we can do in order to solve such a configuration. Again, don't forget, my dear students, that you have the ability to use the assumption that the current flowing inside the operational amplifier is equal to 0. So the current here and the current here are continuous. Let's call this I1 and let's call this I2. So I1 and I2 are continuous. And let's call this point V1, for example. So the voltage flowing in the resistance R1 is typically equal to the voltage flowing in the resistance R2 as far as the current entering the operational amplifier is equal to 0. So the current flowing in the resistance R1 is typically equals to V input minus V1 over R1. This current should be equals to the current flowing in the resistance R2, which is V1 minus V output over R2. As you can see. So using this relation, you can easily say that V, let's write it again, V input minus V1 over R1 equal V1 minus V output over R2. And then just to make V output in one side and other elements in the other side, or before doing this, we have another important relation that we can use in this manner, which is the gain relation. You know that V output is equals to the gain times by V2 minus V1. Please remember, this is the first equation we insert for an operational amplifier, that the output voltage equals the open loop gain minus V2 minus V2 minus V1. So let's write this equation. So V out equals to A times V2 minus V1. And as you know, V2 is connected to the ground. So basically, V2 is equal to 0. That means that V out equals to minus A times V1. Herein, you can make a substitution here, because what you are seeking for is a relation between V input and V1 and V output. So you can easily substitute V1 with minus V output over A. So what we will have is as follows: V input over R1 minus, we will substitute V1 with minus V output over A, then minus with minus is plus, V out over A times R1 equals, then again V output over R2, then we will substitute V1 with V out negative V output over A, then we have negative V output over A times R2, negative V output over R2. This is how that circuit will look like. Then now you reach what you want. You have a relation between the input and the output, just some mathematical rearrangement in order to make this equation somehow more visible. So what we can say is that V input over R1 equals to negative V output, we will have it as a common factor, times 1 over AR1 plus 1 over AR2 plus 1 over R2. This is how this relation looks like. You can make it much more easier if you want, if you make some sort of a common denominator for these for these three terms and sum them in one equation. I think I already have this in my presentation slide, I think. So if you make this arrangement, it will be negative V output over R2 over R1 times 1 plus 1 over A 1 plus R2 over R1. So this is just a mathematical reformulation for the equation, just to make it in a one fraction instead of three fractions. But however, you are not obligated to make it. What is interesting by these students, and this is somehow, we can say that this is somehow expected, that I just need to check something. Yes. I think I make it in a verse manner, so just we can hear like this is V out and this is V in, just to be correct. Okay, I'm sorry, but let's ignore this for a while. We don't need this now. Let's go to this equation and let's see what if A tends to infinity. Let's see here. What if A tends to infinity? If A tends to infinity, then this term will tend to 0, this term will tend to 0, and you will have V input over R1 equals to minus V output over R2, or V output equal minus R2 over R1 V input, which is typically the same what we have done in the first circuit while considering A equals to infinity. So this happens when A tends to infinity. So this proves that this is a correct solution. Here you can understand the difference between the realistic or the finite open loop effect and the infinite open loop effect. So whenever this A is larger, whenever the impact of the term 1 over AR1 and 1 over AR2 is very small, and then you can neglect the effect of these two terms and have this closed formula. Of course, this formula is much easier than this one. That's why we usually prefer to use this one as far as A is a very large number, which is nearly in the most of the cases, or sometimes I say it's already an ideal operational amplifier, so you can freely use A. So this is one of the important examples to examine the impact of having a finite open loop gain with respect to the infinite open loop gain used for an ideal operational amplifier. Now, again, let's go to our presentation slide. And this is typically what we did. When A tends to infinity, we have the closed loop gain in this formula. However, when A is not equals to infinity, you have this more complicated formula. Now, let's go to another case where we are interested in calculating, let me say, the input resistance and the output resistance. Herein, I will consider again that the input impedance for the operational amplifier is infinity, and the output impedance for the operational amplifier is infinity. So I am calculating now the input resistance from this point of view, from the source point of view, and the output resistance from this point of view, from the output point of view. So let's now start investigating how to calculate the input resistance and the output resistance for an inverting operational amplifier. Okay, back again to our whiteboard, and let's start exploring the input resistance of an operational amplifier. Okay, so again, this is our operational amplifier. This is the negative terminal, the positive terminal. This is now connected to the ground. This is connected to a resistance R1, and then we have the input. Again, this is a feedback branch with the resistance R2 and connected to that. Now we are seeking for determining the resistance, the input resistance from the source point of view. I mean, from this point. And as you know, that Rin, or the input resistance, is basically equal Vin over In. Vin is the input source. What about In, the current? We have this current, which is the current flowing from the source. This is In. Now, again, we know that this point is now ground. Now I'm assuming an infinite open loop gain. So this point is a virtual ground. We call it VG, which is a virtual ground. That means that IN is simply equals to V minus 0 over R1, which is V in over R1. By that substitution here, you can find that Rin is equals to R1, because simply I put here V in over, this is V in, of course, just to make the same sentence. So V in over R1, so it will result with R1. Now, where is the problem? Where is the issue here? Why we are investigating this trivial example to say that Rin equals to R1? This is actually very important, my dear, because usually whenever you are designing any amplifier or any circuit generally, you are tending to make your input resistance equals to infinity, so that you can exclude any loading effect from the previous stage due to a potential divider. Then, whenever you have an Rin equals to R1, so in order to reach this relatively hypothetical or ideal configuration, you should make R1 as large as possible, so that you don't have any sort of loading effect on this stage with respect to the previous stage or with respect to the source. Accordingly, if R1 is very large, which is a requirement from the input resistance point of view, this will automatically have a contribution or reflection on the gain, the closed loop gain, which is equals to R2 over R1. So whenever you increase the resistance R1 in order to make this amplification stage ideal, this will automatically affect R1, the gain, as you are lowering down the gain. Whenever R1 increases, of course, gain will decrease. So this somehow limits your controllability, your tunability of the gain. If you remember, we said that the main advantage of the closed loop configuration is it's tunable, it's controllable gain. But now this is not 100% true, because you have another restriction. You need to make R1 very large. So this R1 increase, then the gain decrease. Then this may be one of the major disadvantages of course, this here there is a negative sign. So this is one of the main disadvantages of the inverting configuration, as you can see. Okay, before proceeding to other configuration, we have actually maybe two examples to be solved in this lecture, or this part actually. So let me return back quickly to my presentation slides. We already did this input resistance, and we determined that this input resistance is equal to R1, and now this is the first example. So this is another configuration. We still call this, my dear students, a non-inverting configuration. We still call this a non-inverting configuration because this is, again, you have a feedback branch from the output resistance, from the output terminal to the inverting input terminal. So it's still an inverting configuration. However, the only difference now that you have 3 resistance here in this branch instead of 1. In the previous configuration, you only have 1 resistance. However, here you have 3 resistance in this area, in this equation. So let's now start together solving this circuit and see how we can reach an expression for the gain and the input impedance and the output impedance of the input resistance and output resistance of this configuration. Let's now start this. Again, let me close the share screen and turn to the resistance. Okay. Now we have an operational amplifier. And we have, this is an inverting input and this is a non-inverting. Again, this is connected to the ground. Just need to make sure of terminology. Perfect. Okay, so this is R1 and this is V input. And now we have this branch, which includes 3 resistance. This is grounded, and this is connected to the output resistance, the output voltage. Call this R2, R3, and R4. And what we are seeking for, my dear students, is an expression to express the resistance. Sorry, the output in the terms of input, or what's called again, the output over the input. This is what we are seeking. So again, this, I think in this problem, that this is an ideal amplifier. So please remember, ideal amplifier means input impedance equals to infinity, output impedance equals to 0, no current flowing inside the operational amplifier, gain, the open loop gain, of course, is equals to infinity, the voltage drop on V2 is equals to the voltage drop in V1. Accordingly, automatically in your answer booklet, I would appreciate if you can write that this point is a virtual ground automatically, because V2 is connected to the ground. That means that this is a virtual ground. Now, it's somehow a circuits problem. We have current here. Let's call this current I1. Knowing that no current is flowing inside the operational amplifier, then this current will continue here. As you can see, this current will flow in this direction. So typically, I2 is equals to I1. Makes sense, because no current is going to this branch, so all the current will go here. Then this current at this point will be branched into 2 branches. Some current will flow in this direction, which is I3, and other current will flow in this direction, I'm sorry, which is I4. This is typically a nodal analysis in a circuit problem. So let's start writing the expressions for these 4 currents. Okay. So first, let's start with I1. Let's call, again, we will need this point, so we will call this point Vx, for example. It's an unknown, of course, for our. So I1 is equals to the input voltage, which is Vin, minus this voltage, which is virtual ground, so this is 0 over R1. So it's V1 over V input, except not V1, V input over R1. Then, what about I2? I2 is equals to 0 minus Vx over R2. So it's minus Vx over R2. What about I3? It's Vx minus 0 over R3. So I3 equals Vx over R3. What about I4? It's Vx minus V output over R4. So I4 equals Vx minus V out over R4. These are the 4 main currents conducting in this circuit. Let's now start combining equations together. We know that I1 is equals to I2. Makes sense again, because no current is flowing inside the operational amplifier. And we know that I2 is equals to I3 plus I4. This is a direct branching on this node. So let's write these 2 equations to us. So first, I1 is equal to I2. So that means that V input over R1 is equals to minus Vx over R2. This is the first equation, which is I1 equals to I2. Again, this is I1 and this is I2. So it's direct equality equation. Now, this equation is not enough. Why? Because what you are searching for is a relation between V input and V out, not a V input and Vx. So you need another equation where you can substitute by Vx in terms of V out, which is the second equation. We know that I2 is equal to I3 plus I4. So let's now write it. So minus Vx over R2 equals to Vx over R3 plus, this is I2, this is I3 plus I4, which is Vx minus V out over R4. This is how that equation looks like. So simply from equation number 2, you can have V output in terms of Vx. So as you can see, we can shuffle this term here and get this V output here. So we have V output over R4 equals to Vx over 1 over R2 plus 1 over R3 plus 1 over R4. And then that means that Vx is equals to V output over R4 over all these terms, which is 1 over R1 plus 1 over R2 plus 1 over R3. Now, from this equation, which let me call it 2 dash, from equation 2 dash, you can substitute back here, and then you will get a direct relation between the V input and the V output. Let's see. So what you can say that V input over R1 equals to minus, instead of having Vx, 1 over R2, and then I will substitute by Vx with, so what I did is just, I will kick out this Vx and put all these terms, so which is V output over R4 over 1 over R2 plus 1 over R3 plus 1 over R4, as you can see. So generally, what we can make now, we can say that V output equals to, now we have a negative sign, we have R2 and R4 over R1, and then we have this term 1 over R2 plus 1 over R3 plus 1 over R4, and then this is all times V out. So this is V. So this is a general formula where you have R2, R1, R2, R4, R1, and R3 in terms V output and V input, and then this is now the closed loop gain. This is now the closed loop gain. So you can now control the gain using this equation. Maybe one of you should ask a very important question here and told me, what is the advantage of this circuit? What we have benefit for? If you recognize this circuit, you can say that the input resistance is still equals to R1. So nothing new here. You did not change anything from the input resistance perspective. It's still equals to R1. What is changed is the open loop gain. Instead of having a very simple open loop gain equals to R2 over R1, you have an overall open loop gain which is somehow more complicated, as you can see. The main advantage here is the contribution of R1. In the previous version, you are only controlling the gain using R2 and R1. Now you are controlling the gain using 4 parameters, R1, R2, R3, and R4. So generally, you increase your freedom in order to control the gain with respect to the first configuration, where you have only 2 resistors in order to control the gain. Herein, I invite you, my dear students, to go to our lecture script, where I have introduced a numerical example in order to examine together the effect or the difference actually between these 2 configurations in terms of the ability to control the closed loop. In this example, you can examine how this configuration will make life easier for you in order to control gain with respect to the other. Additionally, I invite you, my dear students, as one of our first bonus questions, to access these 2 configurations using multi-sim and to examine the closed loop gain using the multi-sim with the same values for the 2 configurations, and see how you can control the gain in this configuration and how you can control the gain in the other or the previous configuration where you have only R1 and R2. This is actually somehow very interesting for you. So let's now turn back to another types of configuration. Again, as I mentioned, this lecture is a series of circuits. So we are solving a lot of circuits together. So now we have another interesting circuit. Let's see how it looks like. So we have now our operational amplifier. This is the negative terminal and this is the positive terminal. And again, this positive terminal is connected to the ground. And now you have only 1 resistance in the feedback branch. We call now RF. Okay. And hearing, instead of having 1 input, you have a series of inputs. So, sorry. I have to fix it. Okay. So, for example, let's make it 3. I believe in the presentation slide, they are 4. Okay, they are n, whatever. So let's make it 3 for that. So this is R1, and this is V1. This is R2, and this is V2, and this is R3, and this is V3. So this is a circuit. Again, this is the out. And as usual, we are assuming an ideal operational amplifier. So in this circuit, what we are going to do is that we are going to investigate the relation between the output and the input voltage. Now we have more than 1 input to the circuit. It's not only V in, we have V1, V2, and V3. And we have a single output, so we are just linking these 3 inputs or whatever n inputs with the output. Now, as you can see, this is an ideal operational amplifier. So this is again a VG or a virtual ground. Again, no current is flowing inside the operational amplifier. So if I call this I1, I2, I3, whatever, then in this node, these 3 currents are now come together and flow in the resistance RF. No other option. Okay, so at this point, all these three currents will be added and will directly flow here in RF because no current is flowing inside the operational amplifier. So if I call this IF, for example, that automatically means that IF equals to I1 plus I2 plus I3. As you can see, it's a straightforward way. So by writing this equation, you can just say that the current flowing in this branch, which is the first branch, of course, it's V1 minus 0 over R1. So it's V1 over R1. The current flowing in the second branch is V2 minus 0 over R2. So plus V2 over R2. Plus, again, V3 minus 0 over R3. So V3 over R3 equals to the current flowing here, which is 0 minus V out over RF. So it's minus V out over RF. Now, if you examine this very interesting equation, you will find that the output voltage is the summation of the three input voltages. Of course, with a negative sign, again, because this is, again, an inverting configuration, because we are connecting the feedback circuit to the negative terminal of the input or the inverting input. But that's why we call it the adding or the summer circuit or the summer configuration. We are summing the input voltage. Of course, you can add 5 inputs, 10 inputs, whatever input. You can add whatever signals you need, and then these signals will be automatically added and then multiplied by a negative sign. But please consider a very important note. This is not Darkian adding. This is what's called a weighted adding. Because if you get this RF on the other side, you will find that V output equal minus RF over R1 times V1 minus RF over R2 times V2 minus RF over R3 times V3 and so on. So you are multiplying each input voltage by a weight equals to RF over its internal resistance, and then multiply this with the value of the input. So that's why we call it a weighted summer or a weighted adder circuit, because you make this addition with a certain weight. However, you can easily make this weight equals to 1. So if you put RF, R1 and R2 and R3 equals to the same value, that will result with a fair weighting, and then V output equals minus V1 plus V2 plus V3 plus V4 and so on. If you need to make addition with a variable weights, then you can adjust the values of RF R1 and R2 and R3 and so on. So that's why we call the circuit as a weighted summer or a weighted adder circuit. One of the very interesting circuits dealing with operational amplifier. So in order to terminate this part of the lecture, let's go to the final circuits today, or in this part practically, which is now another configuration. Why it's another configuration? Because we are going to insert the input to another terminal. I mean, our new circuit will look like this. This is the negative terminal, positive terminal, and of course this is the output. We have the resistance. We can call it R2 or RF. Some textbooks call this RF to refer for this as a feedback signal. So let's call it RF. You can of course say we call it R2 or whatever. And we have another resistance here. Let's call it R1. And now in this point, you don't have an input, you have a ground. And your input now is inserted or is connected to the positive term. And of course, this is the out. So this is another configuration where we can use. Let's now see how we can determine the gain of this configuration. So again, please don't forget our 5 important notes whenever you are dealing with an ideal operational amplifier. The input impedance is equal to infinity. The output resistance or impedance is equal to 0. V1, V plus and V minus, or V1 and V2 are equal. The current flowing inside the operational amplifier is equal to 0. So this current is equal to 0. And the open loop gain is equal to infinity. So this voltage equal to Vin, which is automatically means that now this voltage equals to Vin. Again, because that 2 voltage here should be equal. And knowing that no current is flowing inside the operational amplifier, that means that the current here and the current here are equal. Let's call them I1 and I2. So I1 and I2 are equal. Let's write an equation. I1 is equals to 0 minus Vin over R1. So it's minus Vin over R1 equals to the current flowing here, which is Vin minus V out over R1. Oh, sorry, over RF. So using this equation, you can write, you can put V in one side and V out on one side. So we have V out over RF equals to V in over RF plus V in over R1. I pick it here and I get this. That means that V out equals to RF times V in times 1 over RF plus 1 over R1. Okay, now, very important observations. First, V output and V in are of the same sign. There is no negative in the gain now. That's why we call this a non-inverting configuration. Now the input is connected to the non-inverting terminal instead in the previous case. First observation. Again, the gain is controlled by RF and R1, these two resistors. Of course, you can multiply this RF inside, so it will be 1 plus RF over R1, which is somehow more easy. So this is another observation. A very important and critical information. What if you calculate the input resistance of this configuration? Again, input resistance is V in over I in. So this is the input. So in this point, this is the input resistance. It's V in over I in. V in is the input. What about I in? I in is equals to 0. So your input resistance in this configuration is typically infinity. That means that we overcome one of the main disadvantages of the previous configuration, where the where the input resistance was a function in the resistance R1, and whenever you increase it, you affect the gain. Now you have an ideal infinity input resistance without any effect on the gain. So finally, let me return back to my presentation slides. And again, open the pointer. So this is the first example we solved together. And now this is the second example when we reach an addition, a weighted summer in the circuit. And finally, this was the final non-converting, non-inverting configuration for operational amplifier. This is considered actually, my dear students, the termination for part number 2 in lecture number 1, dealing with operational amplifier. In the next part, which is most probably will be the final part, we are considering more and more configurations for operational amplifier, where we can use operational amplifier in more interesting application, right? Like, for example, buffer and inverting, sorry, and differentiator and integrator, and more and more interesting circuits. So let's do it together in the next part. See you next part, inshallah, and have a good day. Bye bye.